Hello everyone, welcome to another Wallet Making Wednesday. Today we're making custom top plates for our magnetic case wallet. As well as we're going to be engraving a custom pattern on the front plate with a 1/16 inch CBD diamond coated end mill. Let's get started in Fusion. Okay, the next part we're going to be making for our case wallet is this top plate here, which your cards and cash go under. It's held together with these two binding posts. And to cut this out, we're going to be using three different operations. We're going to be using 2D Pocket to cut out these small features in here. We're going to be using drill bore to cut out the holes for the binding posts. And we're going to be using 2D Contour to cut out the outer edges, as well as put on the chamfer on the outside, as well as in this 2D Pocket. So we're going to move up here to our palette. So these two plates are what we're going to be doing the cam for today. These patterns were just overlaid on top of the existing plate. So to get these patterns on, I didn't use Fusion. You can use other programs, any other vector program. I use Illustrator specifically. You can upload any type of DXF or SolidWorks file, and what you do is once it's uploaded, you just right click and you can insert into current design, and that will overlay the sketch of the file you uploaded, and you can position that sketch and align it with the geometry of the plate or whatever you want to do the engraving on. So that's how I got these patterns into Fusion. Okay, so we have two different patterns we're going to be engraving first. The one on the left, I'll just call that the hex, and the one on the right, I'll call this the shard. They're both going to be using 2D Pocket with a 1/16 inch tool. So let's get started and select the setup. We're going to go to 2D Pocket, and our tool selection is going to be this 1/16 inch CBD diamond coated end mill. Because the depth here is about 1 millimeter, we're going to be, which is a significant fraction of the tool diameter, we're going to go pretty easy on the cutting feed rate. So our cutting feed rate, 250 millimeters per minute. Our lead in 100, lead out 200, and our ramp, because in 2D Pockets you're going to use a helix to bore into the material, your ramp is what will determine your entry into the material rather than your plunge. So your plunge rate is fairly superfluous in this operation. So now we're going to start selecting our geometry. We're going to select just the top contours in each one of these hexes. And you'll notice that the red arrow is on the inside of these hexes, so the pocket is bounded on the outside by the blue line. So now we're going to click over to our heights tab, and we're going to set our clearance height 10 millimeters above our retract height. That's fine. Our retract height, we want this to be pretty shallow because there's a lot of hexes and we don't want to waste a lot of time in Z-axis movement, so I'll reduce that to 3 millimeters. Our feed height can be nice and low, 1 millimeter. Our top height will just be our stock top. And our bottom height, I like having this at stock top, and then I put in a negative offset. So because I know that I want about a 1 millimeter depth into the face of the material, I'm going to put a -1 here. Next is our passes tab. So our maximum step over, I want this to be about half the diameter of the end mill, just to keep it nice and safe so we don't get any tool breaks. So I'm going to put in 0.8 millimeters for the maximum step over, and I don't need to mess with the stock to leave. The model is pretty much fine the way it is. I'm also going to turn on smoothing. That'll reduce some of our G-code overhead. Next is our linking tab. We're going to set some really nice, small, shallow lead-ins because the features are so small. So we're going to put in 0.2 millimeters for our lead-in, as well as 0.2 millimeters for our linear lead-in distance. Now our helix, we want our ramp diameter to be fairly small, so 1.5 millimeters works. That'll give us a nice small lead-in, or a nice small helix that won't impact the outside edge. And the ramp clearance height, we can reduce this to 0.5 millimeters. And our ramp radial clearance, just to make sure we're not impacting that outer edge, put that to 0.1. And we'll increase our ramp angle a little bit to 3 degrees. Okay, we're going to hit OK and generate that. Okay, so this is our toolpath here. So we're starting off by boring right into the center, and then it moves over in 0.8 millimeter increments. Now that we have a good look at these toolpaths here, I'll also explain a little bit why I chose 2D Pocket instead of something like Adaptive. So the great thing about Fusion, especially if you're new to CAM, is when you hover over the toolpath or the operation type, it will give you a nice little tooltip that explains it. So here in 2D Pocket it says it creates a roughing operation that uses toolpaths parallel to selected geometry. So because this geometry is already in the shape of a hexagon, that means my entire toolpath will follow that entire contour and just keep doing step overs until it reaches the outside. So this is really a roughing and finishing strategy in one, depending on your cutting speed. Whereas if you use a 2D adaptive or a 3D adaptive, the CAM will want to create trochoidal milling paths, which if you have a machine that isn't very rigid, or if you don't have a commercial CNC machine like I do, you're not going to want to mess with extra finishing passes and extra roughing passes when it's not really necessary. So by using 2D Pocket, it will be a little bit slower than a trochoidal milling path, but you'll get a very nice sharp cut on the outside when the operation is finished. Okay, for our next operation, we're going to be doing a 2D Pocket to cut out these small features in here for the shard plate. Now there's a trick in Fusion that you can use to quickly duplicate a toolpath that you know is going to be fairly similar to the one you previously did, instead of starting from scratch again. So I'm going to right click on the operation we just did, go down and hit duplicate, and that will make a second copy of that same toolpath that we can go in and edit now. So all of our cutting speeds and feeds are the same. I'm going to move over to the Geometry tab and just clear all of those pockets from before and start selecting our new geometry. So I'm just clicking the top of the contour at the top of the stock in each pocket. Because we want to make sure we're doing the inside, I'm going to click these red arrows and make sure everything is on the inside. Now in our passes tab, everything is basically the same. We're still going to want that 0.8 millimeter step over. Now in our linking tab, we're going to want our entry helix to be a little bit smaller because these features are quite thin. So in helical ramp diameter, we're going to change that to 0.5 millimeters. So that's just going to basically make this the absolute minimum diameter helix we can do for our entry into the material. Now we're going to go back to our passes tab and we're going to set some stock to leave here. Set our axial stock to leave to 0 and set our radial stock to leave to negative 0.3, just to make sure that because these features are so thin, we're getting enough space. We're also going to turn on feed optimization. And we want our reduced feed radius to be larger than the largest radius in our feature. So if we set this to 3 millimeters, that should easily cover all of the corners that the tool is going to be moving into. Our reduced feed distance, we're going to set this to 2 millimeters. And our reduced feed rate, we're going to set that to 150. And we're going to turn off only inner corners. Okay, let's hit OK to generate that. Okay, now here we see this green line in here, which is essentially a rapid along the path of the feature that doesn't elevate above the material. And we can see that this line comes kind of close to this outer toolpath. So that makes me a bit nervous. So we're going to go back into the operation, go to our linking tab, and unselect Keep Tool Down, and hit OK. So now instead of moving that rapid along the inside of the feature, it's gone back up to the feed height. Okay, next we're going to move to our 2D bore, or sorry, our bore for our binding posts. So we're going to click Drill, select a 1/8 diameter tool, and start setting some speeds and feeds. So we're going to max out our RPM at 24,000. Our cutting feed rate is going to be 800. Lead in and lead out doesn't really matter for this toolpath because it's ramping in. Our ramp feed rate, we're going to set that to 600. Okay, let's start selecting geometry. So now we're going to start off with these inner hole faces. Whenever you're doing a counterbore, it's best to do the inner face first, in my opinion. It makes the cutting of the counterbore a little bit easier and faster. Okay, here in our clearance tab, our clearance height's 10 millimeters, that's fine. Retract, that's fine too. Our feed height, we want that fairly close to the material to save time. Set that to 1 millimeter. Our top height, because this is recessed into the stock, we're going to make sure our stock top is selected because we don't want it just doing a rapid right into the top of the material. And for bottom height, we're going to leave it on hole bottom and then just put a -2 to make sure we get a nice edge finish on the bottom hole there. Our cycle type is going to be bore milling, and again, just like your operations in Fusion, just by hovering over it, you're going to see a tooltip that will describe each operation. We're going to set our pitch to 0.5 millimeter and our diameter to 6.15 millimeters. Hit OK. Now for our next operation, we're going to do the same trick we did before, and we're going to duplicate this operation. We're going to move in and edit, go to our geometry tab, clear our previous geometry, and select new hole faces. Now we're going to change our clearances. Instead of bottom height, instead of hole bottom for our bottom height, we're going to have hole top. And then our offset is just going to be -1.6, which is our depth from the top of the stock. We're going to keep our pitch the same and change our diameter to 11.3 millimeters, which is the outer diameter of the head of the binding post, and hit OK. Okay, now our next operation is going to be another 2D pocket for these large pockets in here. So we're going to select 2D pocket. Our Endmills is already selected. Our cutting feed rate, we're going to reduce this a little bit to 600 millimeters per minute. And change our lead-ins to something nice and easy. 100 for lead-in and lead-out. Our ramp, because we're going to be doing a helical bore into the stock, we're going to keep this pretty high at 1000. Now we're going to start selecting our pockets. So we're just selecting the top contour in each pocket. So we're going to move over to our heights tab. Our clearance and retract are good. Our feed height, to save time again, set that to 1 millimeter above the top height. And our bottom height, we don't want selected contours. We want this going all the way through the material, so we're going to hit stock bottom, and our offset will be -2 millimeters to make sure we're going all the way through to get that nice edge finish. Okay, next we're going to go into our passes tab. And before I mention, one of the great things about 2D Pocket is that you can combine your roughing and finishing passes in one operation. So we're going to start off with our roughing section. Our maximum step over, we're going to make this fairly aggressive at 2.5 millimeters, which is a fairly significant fraction of our tool diameter. We're going to have some radial stock to leave. Set this to -0.2. That's just based on experience, based on how many times I've run this operation. And we're going to turn on smoothing. Now we want to do a finishing pass on the outside to make sure we get a really good edge finish there, and make sure our chamfers for our next operation will be nice and accurate. So we're going to turn on finishing passes. We're just going to use one finishing pass, and our step over, I'm going to set this to a nice even number, like 0.5 millimeter. Our finish feed rate, we're going to lower this down to 200 millimeters per minute. And this basically means that it's going to look at the outer contour that you've selected, and it will end the last roughing pass 0.5 millimeters away from that edge, and then for that last finishing pass, it will take off that last 0.5 millimeter, disregarding this maximum step over value. Next, we're going to turn on our feed optimization. We're going to set this to a nice high value to make sure we capture all of our radii. Our reduced feed rate distance, I'm going to set that to 2 millimeters. Our reduced feed rate to 400, and we're going to turn off only inner corners. So let's move into our linking tab now. Okay, we're going to go to our lead-ins and lead-outs. We want to make sure we're well away from the edge to make sure we don't impact that and mess up our finishing pass. So we're going to set that to 1 millimeter. And for our ramp helix, we want to change this down to 1 millimeter just to make it a little bit faster. This ramp clearance height essentially adds to your feed height. And 3 millimeters is fine for our helix diameters. So we're going to hit OK and generate that. So if we hit the top view, that will give us a nice way to see our finishing passes. So we can see here our roughing pass ends 0.5 millimeters away from the outer contour. And on both operations, we have our feed rate optimization slowing into the corners as it turns around. Okay, we have a little yellow exclamation mark here. That's lifting feed plane to topmost ramp. That's a fairly common one. It really doesn't actually impact your toolpaths much, but to get rid of that, I'm just going to go into our feed heights and increase this to 2 millimeters. And that should get rid of it fine. Okay, next we're going to cut out the outside of these wallet plates. So we're going to use 2D contour. Our tool's already selected. Our feed rates are going to be fairly quick, 600 for our cutting feed rate, and we'll increase our lead-ins and lead-outs a little bit. Go to your geometry tab and select the outside contours, making sure the red arrow is on the outside. We're going to turn on tabs. Click at points instead of by distance. And we're going to start clicking where we want our tabs to go. It's easiest to do this in the top view. So we're going to put 3 tabs on each plate to keep that nice and secure. Now our tab height, keeping in mind that we're going to be plunging down about 2 millimeters below the stock bottom, so our tab height has to include the stock bottom. So if I take off 2 millimeters from here, that leaves a tab height of about 1.5 millimeters for the G10, which should be fine. For our tab width, we'll just leave that at around 3 millimeters. That should be sufficient. Next, let's move into our heights tab. Our retract and clearances are okay. Our feed height can be 1 millimeter. And our bottom height, stock bottom, -2 millimeters. Let's move into our passes tab. Off the bat, I'm going to turn on smoothing. Turn on feed optimization. A reduce feed radius. We want to slow down on these very large radii corners, so I'm just going to set this to an arbitrarily high value of 10 millimeters. And a reduce feed rate distance to 3 millimeters, which is basically the distance that it will slow the feed rate down to before it hits the start of the radius. Turn off only inner corners and reduce this to 300 from 600. We're just going to be cutting this in one depth of cut. We're not going to be taking any multiple passes. So let's move over to our linking tab now. We're going to set some fairly easy, shallow lead-ins and lead-outs. So in case there's any deflection while we're entering the cut, it will enter at a fairly nice shallow angle. So we're going to set that to 45 degrees. Now for our entry positions, I like starting the lead-ins and lead-outs over top the tabs, because I'm going to be grinding those tabs off in case there's any type of tool deflection as I'm entering the stock. It'll just get ground off while when I take the tabs off at the end of the operations. Let me hit OK to generate that. Okay, so here are our 2 2D contour cuts. Our last operation is going to be a chamfer. So we're going to go to 2D contour again, and we're going to select our spot drill, which is essentially just a diamond coated drill point Burr end mill. We're going to move that to our maximum RPM. Cutting feed rate 600, same as our contour. And we're going to start selecting our outer geometries, as well as our inner geometry. Our heights tab can all stay as default. Because the chamfer is happening right on top of that contour, we can leave our bottom height at selected contour. Moving over to our passes tab, our chamfer width is going to be about 1.4 millimeters, and our chamfer tip offset is going to be 0.5 millimeters, just in case there's any deflection. We're going to also turn on smoothing. I'm also going to turn on feed optimization just to make sure those outer radiuses are nice and accurate. So we're going to set that to 10 millimeters and 1 millimeter. Slowing that down to 400 from 600, turning off in inner corners. Moving over to our linking tab. I'm going to set this to a fairly high value, 3 millimeters, to give it a lot of space to lead in. And our entry positions, just like our previous 2D contour, I like to start the entry positions right over top of our tabs. And for these pockets, I want to start our entry position right in the middle of the widest part of the contour to make sure that large 1/4 inch end mill doesn't accidentally bump into any of the narrow features. We're going to hit OK to generate that. Okay, some things I'm going to change. I'm actually going to reduce that radius a bit. Or sorry, I'm going to reduce that lead-in distance a little bit. Okay, there we have it. So that's all of the operations for our case wallet top plate. Just to make sure that we haven't done anything crazy, we're going to simulate that entire thing. Turn on stock, and we're going to use tail. Flip that around to how you're going to see it in the CNC machine. So here we have those hexes being cut out. You can see the step over happen, and you can see that the inner radius of each of the hexes is the same radius as the tool diameter. In the model, if you just leave the corners nice and sharp in your model, you don't actually have to go through all the trouble of adding a fillet to each one of those features in the model, which can take forever. You can just leave the corners sharp. The cam will take care of the rest, and what you'll end up having is a corner that will have the same radius as the tool diameter you're using. We're just going to speed through this. So we can see it here taking that last finishing pass off the edge, just in case there's any tool deflection. So if you really tweak your cam and have good finishing passes, there's no reason why a DIY machine like an Openbuilds C-beam can't do some fairly nice part finishes. Okay, I think that's good enough for the simulation. We've seen one get fully cut out. Thanks a lot for watching. I hope you're able to learn something about Fusion 360 Cam and about the 2D pockets and the advantages they might have over adaptive. Next, we're going to move right into the CNC cutting.